100 billion. According to a lab at Yale, researchers estimate that the human brain consists of 100 billion neurons. To put this into perspective, there are more neurons in your brain than there are stars in the entire Milky Way. Additionally, your brain generates enough electricity to power a small LED light bulb. Hello, my name is Evan Kolberg, and today I will be presenting my research on the identification of excitatory and inhibitory EAT neurons for frequency regulation of network activity via HDMEAs. Multi-electrode arrays, commonly referred to as MEAs, are devices that researchers use to record electrical signals from neurons and also stimulate neural activity. Now, bursting refers to the rapid succession of action potentials, also known as spikes, that spread throughout a culture like a ripple effect as they influence other neurons. As this happens repeatedly, the synaptic pathways strengthen between neighboring neurons. This phenomenon is used for training. In regards to bursting, a neuron is either considered excitatory or inhibitory. Excitatory neurons start bursts, and inhibitory neurons stop them, preventing them from continuing forever. Now, earlier MEAs were very limited and yielded fragmented recordings of neural activity. With modern improvements in MEA technology, researchers can also record more accurately, faster, and for longer. However, many modern methods of identifying excitatory or inhibitory neurons came with drawbacks. That's why it was my goal to develop a novel method of classifying neurons as either excitatory or inhibitory, purely using recordings of network activity and complex data analysis. Then, if the functions were successfully implemented, the method should be used in an experiment to display its viability. The experiment is referred to as the frequency game, where cultures are continually stimulated and respond by sending bursts to certain areas of the MEA chip that enclose the most excitatory and inhibitory neurons. The cultures can then adjust the frequency of stimulation. Throughout developing the analysis functions, I used neurons that were microsurgically dissected from E18 rats. Once the neurons were put onto MEA chips, they were kept at 37 degrees Celsius, 5 degrees CO2, and 95% humidity. To develop the following functions, various recording files were used, and the analysis was performed in Python. In each data file, 1020 to 1024 neurons were recorded at 10,000 kHz, or 10,000 times per second. Before processing any data from a culture, it has to be cleaned and simplified. This will reduce any noise and inaccuracies from within the data. Also, it ensures that the MEA machine records all the data correctly. This works by iterating over each spike within a time bin of 1/100th of a second and converting it all to a binary matrix. The next step is to determine the quality of the data. The Hamming distance is calculated to quantify the difference in spike patterns between channels. Then, the physical Euclidean distance is calculated between each channel, measuring how far apart they are. On the left, the Hamming distance values are shown on the x-axis, and the frequency is shown on the y-axis. On the right graph, the physical distances are plotted on the x-axis, and the Hamming distances are plotted on the y-axis. The next step is to calculate the co-firing probabilities for a single channel to all other channels. This entails quantifying the chance that two channels will fire within a 21 time bin window. The generated heat map will show synchronous activity and average behavior. This is done by iterating over all the data and calculating the probabilities. The above subplot is a heat map of all the probabilities, where a lighter color shows a higher co-firing probability. The below subplot shows this as an average. Just as this was done for one channel to all channels, the next step is to calculate the co-firing probabilities for each channel to each channel. Channels are then plotted on the y-axis, and time bins are plotted on the x-axis. Essentially, each row of the heat map shows a condensed form of the bottom subplot from the co-firing probabilities for a single reference channel. The next step is to generate a binary matrix form of all the probabilities. The algorithm will identify peak firing times for each channel. Then, the co-firing probability heat map for all channels will be sorted to show which ones are likely to be excitatory or inhibitory. Here, this shows the co-firing probability heat map sorted. Additionally, this can be sorted by distance from a single reference channel. The slope of the line that emerges from the peaks shows a directional flow of bursts within the culture. To show that the aforementioned algorithms can be used as a practical tool for researchers, I utilized it in an experiment called the frequency game. Cultures are continually stimulated and respond by sending more bursts. When these bursts enter square regions on the chip, this counts as a button press. The goal is to see if they can balance these buttons and achieve a desired frequency. Once that is done, further analysis will take place. Probability of button A presses was plotted against stimulation levels, showing a balance between the two buttons across cultures. At the lowest stimulation level, 0.02 Hz, the button A press probability was scattered, suggesting the physical location of the buttons influenced behavior. At stimulation levels 5 through 9, the probabilities converged to 50%, indicating cultures have successfully balanced the buttons. By stimulation level 10, 2 Hz, probabilities diverged, with ideal balancing observed between 1 to 1.8 Hz. Using the excitatory and inhibitory classification algorithms, it was observed that the experimental group, cultures that received no stimulation, followed a very natural fluctuation between excitatory and inhibitory counts. The experimental cultures experienced irregular behavior. Having few cultures available limited the scope of this study. Because of the similarity between cultures, potential biases might exist. A future study should track the excitatory and inhibitory counts over a much longer period of time. This will provide more insight into neural mechanisms. Additionally, a machine learning approach should be applied to further build upon the methods of classification. These are my acknowledgements. These are my references. Thank you.